Okay, good afternoon, everyone. Welcome to today's fifth EIG webinar to be given by David Cragg from AECOM on remediation of contamination from chromite ore processing residue to aid brownfield development in Glasgow. My name's Alex Finley and I'm on the committee of EIG. Just a couple of notes before we start. All previous webinars and this one will be available on our YouTube channel, and there's a link to that at the top of the chat box. Feedback and volunteers are always welcome for future webinars. Please do not hesitate to get in touch. Contact details are available on a website. Again, there's a link to this in the top of the chat box. Today's talk will last approximately 30 minutes, giving time for a good question and answer session afterwards. If I could just ask you to type any questions you have in the Q&A box rather than the chat box, as this makes it easier for us to see them. And with that, I'll pass over to David.
Thank you. Good afternoon, everyone. So I'm David Cragg. I work for AECOM. I'm a technical director in remediation design, and I'm going to take us through the work that AECOM and legacy companies have carried out at the Shorefield site in Glasgow. In the opening slide, you can see the red line which defines the Shorefield part of the Clyde Gateway regeneration area. Before we get into the details, I want to acknowledge the involvement of the various project team partners, particularly Clyde Gateway Developments Limited, Turner Townsend Project Management, AECOM and its legacy companies, the main contractor for phases 1 and 2, VHE, and their subcontractor Provectus, suppliers of some of the chemical additive, Sagaseki, the analytical laboratory SAL, and our regulator partners, South Lanarkshire Council and Scottish Environmental Protection Agency. And I also want to take the opportunity to name check present and former colleagues in AECOM who've had a major input to this project. In particular, my current colleagues, Jen Niven, David Gemmell, David Granger, and in particular, a former colleague in AECOM, Dr. Richard Bewley. And he has been central to all of the work that's been carried out on this project for well over a decade. So the content of my presentation, I'm going to take us through the geological context and the industrial legacy, the characteristics of chromite ore processing residue, or copra, the investigations and options appraisals and the remediation strategy that we've provided, how the remediation process has been implemented to date, and very importantly, for the future, are there sustainable alternatives to the way we've approached this project? So the Clyde Gateway project covers a very large area of the old industrial part of East Glasgow. And within that, the Shorefield master plan boundary covers an area of about 60 hectares. So we're located to the south of the River Clyde and just to the north of the M74. The Shorefield site contains existing industrial estates and the Shorefield Greyhound Stadium. And Clyde Gateway's objective is to deliver a major business district as part of the regeneration of this part of Glasgow. Now, in Shorefield, between the 1850s and the 1960s, over 1 million tonnes of copra was used as infill in engineering materials in southeast Glasgow, not just Shorefield, but the wider area. And the key contaminant that we're dealing with here is hexavalent chromium. So I thought we should, given most of us are geologists or variations on geologists, a context here for the source of the chromite ore. So this is from a US Geological Survey review. We're dealing here with what's known as podiform deposits, which occur in ophiolite sequences in various parts of the world. So where the chromite is relatively concentrated, it does form a solid solution series with other minerals, but in its mineral form in ophiolites, it is essentially trivalent chromium, which is largely insoluble for all intents and purposes. Now, from the 1820s, the industrialists J&J White offshore field imported chromite ore from deposits of this sort, mostly mined in Turkey and Russia, to manufacture bichromate of potash and soda for use in a number of industries, tanning, dyeing, and so on. Once the ore arrives at the manufacturing facility, it has to be processed to extract chromium. And the traditional approach is summarized in this diagram. And you'll note that crushing, drying, heating, pH control, and so on produces some crystals of chromite salts, but also it appears to be highly inefficient as it produces processing residue with up to several % of chromium remaining in it. The main thing to know here is that copra waste, in containing percentage levels of chromium, now contains a mixture of not just trivalent chromium, but now hexavalent chromium. So there are various minerals, some of which do occur in nature, but have been, in effect, synthesized in this process, which form copra. And there's a whole list of those minerals here. Now, some of those minerals contain chromite, which has somehow avoided the processing effects, and the most important minerals contain hexavalent chromium. So we have things like hydrogarnet, hydrated calcium aluminium silicate, and hydrated calcium iron silicate containing hexavalent chromium, and a clay mineral which holds chromium-6 in between the layers of the clay layers. All of these substances occur at various relative concentrations in copra, and it can vary very widely, but essentially chrome-6 becomes the most dominant species. Now, this material has arrived from its originally mined state, is being processed, and then is dumped as waste into our local geology. And at the Shorefield site, we have made ground, not all of which is copra, but contains copra deposits. And the made ground overlies a complex sequence of raised alluvial and marine deposits and glacial deposits. The most prominent glacial deposit is the Wilderness Till, and due to glacial scouring and then deposition, the bedrock sequence isn't reached until we get to in excess of 25 meters in this locality. It's worth noting that this is not layer cake stratigraphy. We have gaps and windows in the Wilderness Till formation whereby the Paisley formation can lie directly on bedrock. And also that the Bridgeton sand member is not uniform in thickness and does pinch out. So what are the consequences of copra deposition and weathering? So as I've already mentioned, trivalent chromium is only sparingly soluble and of low toxicity, and is also a nutritional essential at low concentrations, whereas chrome-6 is highly soluble and mobile and is a very significant toxicity and is a known human carcinogen. It's present in nodules, in all size fractions within copra, and the pH of the copra is very high as a result of the presence of the minerals that I spoke about earlier. As environmental engineers, remediation engineers, and risk assessors, we have to address in a development context, what are the plausible routes of human exposure should the site be redeveloped for a change of use? So routes of inhalation, ingestion, and skin contact are key routes of exposure if we're coming into contact with copra. But crucially, hexavalent chromium is known to be very toxic to aquatic biota, and the release of Chrome-6 to groundwater as chromate and dichromate, leading to pollution of groundwater and receiving streams and rivers, is the key issue to tackle in this remediation project. So you might think that the image on the right is some kind of Photoshop, but that's a real image of the Polmedy burn in Shorefield, receiving water for copra residue that's been leached out and transported in groundwater. The image on the left is the copra in situ. The speciation of chromium-6 and chromium-3 in groundwaters can be looked at via a redox assessment, and this is a conventional EH-pH diagram of the chromium species that we can find in groundwater. So Chrome-6 is the dominant form under aerobic and near neutral to alkaline conditions. Chrome-6 is the more toxic and soluble, as I've mentioned. But we then need to look at mechanisms to reduce Chrome-6 to Chrome-3, given this stability diagram. So we could obviously lower the pH. So if you move the pH from top right to bottom left, we can reduce Chrome-6 to Chrome-3. There are other mechanisms to create reduction. So soil organic matter could be added to reduce iron from trivalent to divalent, which then allows reduction of Chrome-6 to Chrome-3. We could also increase the concentration of dissolved iron to aid reduction, or we could introduce other reductants. And there's a lot of literature available on various mechanisms to reduce Chrome-6 to Chrome-3 from wastewater technology and other technologies, which you may find of interest. So the development of our remediation strategy, clearly based on detailed site investigations and upon many years of industrial and academic research going back more than a decade. And again, I would name check Richard Bewley, who was central to the research that was undertaken to develop the remediation strategy. And to carry out, in conjunction with the strategy, a detailed quantitative risk assessment for controlled waters, given that's our main receptor of concern. Our overall objective is, as I've mentioned, to reduce Chrome-6 in the saturated zone, that we can reduce the risk to the River Clyde and to the deeper groundwater, and hopefully to eventually rid surface waters of the green leachate that you saw so graphically in that earlier slide. For the phase 1 works of this site, the output from the risk assessment indicated a risk-based target of less than 1 milligram per litre of Chrome-6. Now, bearing in mind that in the phase 1 area, concentrations in the ground and groundwater are in the tens of milligrams per litre. So there's a fairly big gap between a risk-based target and the concentrations prevalent in groundwater. And then a longer term remedial goal in phase 1 for total chromium to be no higher than 0.9 milligrams per litre for phase 1. So how do we identify a suitable reductant? Again, there have been quite a lot of publications and technical bulletins on various options, and I would direct you to Clare Technical Bulletin 14 from October 2007. Again, Richard Bewley was author of that. And there's been quite a lot of research that we have entered into in collaboration with academia that looks at how to identify reagents suitable for this problem. And eventually we arrived at a plan to apply calcium polysulfide or lime sulfur as the reductant. And there's the equation, the redox equation that results in the reduction of chrome 6 to chrome 3 by applying calcium polysulfide. So again, looking at this diagram, we're going diagonally down from the top right into the center towards the hydroxide, which is chrome 3, as a result of applying calcium polysulfide. So bench scale and ex situ trials were carried out some years ago to prove that this was a successful approach. I've inserted a note here about there being different and variably reactive forms of calcium polysulfide depending on the source of that material. So the US based product is called Calmet, and that is essentially CaS5. There's another product known as Earthcare produced in Japan, which has a wider range of speciation, and both have been trialed and proved to be successful. So just a snapshot of some of the investigations that we carried out some years ago that have been published elsewhere. The concentration of leachate, hexavalent chromium in leachate versus leachable total chromium has a nice straight line relationship, whereas in comparing chrome 6 in eluate versus chrome 6 total chromium in soil, the relationship is far from straight line. And this is probably to do with the mineral speciation in copra and the variation of mineral speciation in copra and how it releases or holds on to chrome 6, depending on shielding and so on. And then top right is the results of some trials using Earthcare calcium polysulfide, and to establish what is the dosing rate that may be required in litres per tonne to arrive at the required level of reduction. So you can see that when you get to somewhere between 1 and 1 and a bit litres per tonne, we're heading towards 90% reduction in chrome 6. Moving from the lab and the bench scale trials into field trials, there's a very good publication. Again, Richard Bewley is the author, Clare Bulletin TDP 30, published in 2013, reporting the results of field trials and how to apply the reductant to the ground. It's one thing to prove it in the lab, it's another thing to prove practicality in the field. So calcium polysulfide being delivered to the saturated zone below the shallow source, groundwater recirculation, augered soil mixing, and direct injection via push probes. Eventually, the direct injection approach was taken as being the most cost effective. Just bear with me a second. So, summary of remediation strategy in what we call phase one. Phase one was an area close to the existing Shorefield Stadium, which is shown on the first slide. So the key elements of the strategy were to reline and reculvert watercourses. These are culverted watercourses which are dilapidated and therefore allow have a connection with groundwater and therefore are short circuits for Chrome-6 laden waters to reach the River Clyde. And you can see on that shot the Polmadie Burn, which was the image with the green leachate. So that's a key part of the strategy, is to reline culverts and watercourses to try to limit, if not completely completely stave off the connection with Chrome-6 laden groundwater. And then to manage the human health exposure pathway related risk by capping the site and to reduce infiltration into the ground and to sever those human exposure pathways. And then in situ treatment of the source area of copper with calcium polysulfide. Allied to that, we have also established monitoring of what we call potential natural attenuation. So where conditions are favorable to the reduction of Chrome-6 to Chrome-3 could be then followed by precipitation back the trivalent hydroxide in areas of more moderate pH. So pH has got to drop to around the 7 to 8 range before that could happen. So here's phase one. You can see the stadium in the bottom left and the Clyde running from top left to bottom right. So you can see the site's being cleared, mostly cleared of surface obstructions. And then implementation of phase one. Here's the summary. So we're injecting the reductant calcium polysulfide via a grid of injection holes, which are formed by percussive rods drilled with a conventional rig using steel rods with a sacrificial tip. The grid is on a 2 meter triangular grid. So the target depths range between the 2 to 4 and in the 2 to 7 meter range. So we're into the groundwater containing the copra. The injection is fed from a store and distribution center for the Casex, which is shown on the screen at the moment. The Casex has to first be diluted to the required concentration, and then it's distributed to the rigs. And here are the rigs working away. So the rods are, they reach the target depth, the sacrificial tip is dropped, and then injection begins in lifts of 200 millimeters under a nominal pressure, which is controlled back at the distribution center. So the pressure is aiming to overcome any resistance at the particle level, but it's not sufficiently high to cause hydraulic fracturing. And once the chemical's been applied to the design volume, the holes are backfilled with bentonite pellets. So we operated what we call a traffic light system to track the success or otherwise of the injection process. So green, we injected the required quantity of reductant. Orange are areas of potential doubt, and red is where we didn't achieve the required injection. So on the red traffic light areas, we have to go back to re-inject. So these are just shots of the sub-areas within phase 1. And in this example, in the western area of phase 1, 163 injection points, with the target zone is about 4 meters thick in this case. There's another sub-area of phase 1 and the third one. So in phase 1, there the sub-areas are, there they are together. And of course, if we're injecting a reductant into the ground, we'd also got to establish that it's not in itself causing an adverse environmental impact. So a lot of monitoring was carried out daily to establish any indicators that calcium polysulfide was reaching the river. And there was no evidence in phase 1 of any ingress during the works. So statistics that we collect alongside the contractor to demonstrate that we're achieving the objectives of the remediation. And you can see the average application rate of Casex on the right there, which is broadly in line with the diagram I showed you earlier, the bench scale diagram. So just over 1 litre per tonne. And again, confirmation that we can, after treatment, we can achieve a very high percentage of reduction in Chrome 6 concentrations in groundwater. Again, that's we're talking there in terms of 83 to 99% reduction in Chrome 6 after treatment. Also, total chromium concentrations, so including hexavalent and trivalent, also showed a very steep decline after treatment in phase 1. And sulfide concentration before and following treatment, again, indicators of whether we have caused another adverse impact as a result of applying this substance. So in phase 1, the conclusions are good, 90% reduction in Chrome 6, and with total chromium following a similar trend. The secondary evidence through the trend in sulfide and to a lesser extent calcium. Leachable chromium in soils, which is also an important factor, was shown to be reduced by around 70%, given that clearly ongoing leaching of Chrome 6 from soils above the water table could continue, but the treatment is shown to have reduced leachability by a very high percentage. And the ongoing strategy of natural attenuation, which obviously involves quite extensive and detailed ongoing monitoring of borehole wells around the site and along the periphery. Now, very quickly, in phase 2, which is in a slightly different area of the site and closer to the Clyde, we carried out the same sequence of work: desk studies, investigations, risk assessments, ground investigations, and refinement of the remediation strategy. But fundamentally, it's the same strategy. However, there are some differences. First of all, the concentrations of Chrome 6 in phase 2 are not just tens of milligrams per litre, but more like hundreds of milligrams per litre. So the challenge is greater. And we found that it was advantageous to apply an enhancer before the calcium polysulfide is applied. So we arrived at the idea of applying ferrous sulfate as an enhancer prior to the calcium polysulfide injection. So in this case, in phase 2, as well as the 2 meter triangular grid network of calcium polysulfide injection points, there were center points of ferrous sulfate injection, which was done prior to calcium polysulfide injection. So in general, we only applied ferrous sulfate as an enhancer when the starting concentration of chrome 6 was more than 100 milligrams per litre. So we've gone up a level in the challenge. Probably the biggest challenge was ground conditions in phase 2, which is ongoing. So we had far more red traffic lights in phase 2 due to obstructions, and we also had a very highly variable formation permeability, which also led to more widespread red traffic light zones. So in the end, we had to review the method of application. So we applied the push probes across the whole area, but ended up with a lot of red. And we returned to those red areas using infiltration trenches. So we're aiming to open up the formation, overcome obstructions, so expose more of the formation to the chemical. So here we are targeting the red zones, and the trenches are designed to just touch the water table and not go below it. Again, this is an example of a trench in process, and you can see there's the green tinged leachate appearing, and you can see the copper just under the bucket as well, this sort of lime green colour. To further open up the formation, we had the base of the trenches augured, 150 mil diameter augured at 1 meter centres to a further depth of 1 meter to try and open up the formation. And then for safety reasons, we backfilled the trenches before the chemicals were applied, and we inserted some riser pipes, as in the bottom right photograph, to be able to monitor the level of the chemical and how quickly or otherwise it was infiltrating into the groundwater. So the results of phase 2 are still subject to ongoing validation monitoring. We're reasonably optimistic that we will achieve targets, but that is on the proviso that the validation monitoring confirms that it's worked successfully. Now, having spent so many years investigating, researching, and then applying a remediation strategy, we're recognizing, all the project partners are recognizing that what we're doing here is leaving chromium in the ground. We're reducing it and immobilizing it and precipitating it, but we're not removing chromium from the ground at the moment. So given that there are further large areas of shore field with even bigger challenges, with chrome 6 concentrations in the thousands of milligrams, not just the tens or hundreds, but the thousands of milligrams per litre, is it time to look at a circular economy approach? And we believe it is time to consider it, as do our partners at Clyde Gateway and SEPA, and particularly SEPA prompted this review. Could there be a market for recovering and recycling chromium from the ground? That's the first question. And if there is a market, how are we going to do it? There's chromium in leachate, chromium groundwater, and of course the copper source still contains percentage levels of chromium. Going back to the process diagram, a very inefficient process was applied that resulted in chromium-rich waste being placed on this land. So we're very hopeful that there will be a process of research into whether it can be recovered economically, and therefore can it contribute to a circular economy approach. That concludes my talk. Thank you for listening.
Thank you very much, David. Certainly very interesting. We've got a few questions for you. The first one, just how prevalent is the problem of this Chrome 6 waste across the UK? Is it just a localised area in old heavy industry areas, or was it across the country?
Going back to the time of J&J White, they established themselves with a virtual monopoly on processing to produce the salts that they produced for dyeing and tanning. I believe there were one or two other competitors, but J&J White completely dominated the market. So whilst chromium will be present in other industrial areas, so I think fundamentally the answer is it is present, but there's an order of magnitude step up to the situation at Shorefield because of the monopoly they had, and therefore because of the over 1 million tons of copper deposited.
Another one, were there any confirmed health effects observed that could be linked to the presence of Chrome 6 in the waste, e.g. workers who deposited the waste as infill, nearby residents prior to remediation?
Yes. Going back to the time of J&J White, so if we're talking about occupational exposure, my understanding is that there was some very coarse and local population, and whether there are known health effects in the many decades following, I have to confess I don't know, but given that we know that Chrome 6 is a known carcinogen, if it's been exposed, which it has been, on the ground, and does it create dust that can be inhaled and so on, then the health effects are pretty obvious. But in terms of occupational exposure, people working in the original factory and dealing with the very dusty environment, there are some very severe health effects that are known in the area, which I'm almost hesitant to say exactly what the effects were, but they're very well known in the local area.
What is the risk of the reduced chrome oxidizing back to Chrome 6 again? Is the pH good enough controlling factor?
We think the pH is a good controlling factor, but I think that the principle around monitored natural attenuation is to prove that is a sustained condition. We've clearly shown that you can get very dramatic levels of reduction down to the trivalent form. But I think it's fair to say that monitored natural attenuation would prove that. And I'd also say that, again, from a personal point of view, it wouldn't be out of the question to go and resample the ground in the areas where reduction has been shown to be effective, and to establish what the mineralogy has become. That is not an unreasonable thing to do. It's not, as I understand it, not currently part of our programme, but I don't see why it can't be done. The other point to make about the threat of, or the risk of a reoxidation is that for various commercial reasons, we've dealt with phases 1 and 2 in the tens to hundreds of milligrams per litre range, but the next phase of Shorefield is in the thousands, and we think that next phase, the chrome 6 may come from a different source. So rather than copra as we understand it, the much higher levels of dissolved chrome 6 may come from other features, tanks and ducts and so on, not the copper itself. So I don't think you can say there's an absolute certainty that there won't be reoxidation, but the indications are that the process has been effective. Yeah.
And I suppose following on from what you've just started saying, in the phase 1 and 2 area especially, do we know what minerals the chrome 6 is leaching from?
I don't think we do know precisely which minerals they're leaching from. We know the group of minerals from one of my earlier slides, which talked about hydrogarnet and so on, which are known to contain the chrome 6 preferentially. So we've got some idea. I know that John Farmer at the University of Edinburgh did a lot of research on the mineral, the speciation, and therefore where was chrome 6 preferentially leaching from. So there's some indications there, but how far that's gone, I'm not too sure, to be frank.
Okay. And is the calcium polysulfate process producing any sulfuric acid?
We don't think so. Again, lines of evidence suggest it doesn't produce sulfuric acid. Well, it doesn't produce sulfuric acid that can be detected on the downstream side of the treatment. It is going to produce acidity, because otherwise, how can we move the pH across the phase diagram? So it must produce some acidity to be effective, but in terms of producing sulfuric acid, I don't think we've got evidence that that's occurred.
And is there a cost-benefit threshold to determining the viability of recycling the copper waste?
In terms of my final slide about the future, there will be. The research hasn't started, but there will be a cost-benefit analysis element to that. And again, just spinning out some ideas. At one end of the scale, you could say, okay, well, we could technically excavate all the copper. We could systematically move across the whole area and excavate, in effect, remine chromium, in effect. But that's a massive undertaking, which would require deep holes in the ground, dewatering, and then backfilling. So is that cost beneficial? My initial thought is possibly not. At the other end of the scale, you could look at just recovering the dissolve phase. So you could take a mine water treatment related approach, whereby you accept that the leachate is going to find its way to watercourse, but then capture it in a wetland and generate a sludge that's very rich in chromium. So they're two. I'd see those as almost two end members of the possible approaches to recovering chromium. But when you get into cost benefit analysis, it's not just about the cost of operating the process versus how much chromium you win. it's what if you don't win it and leave chromium the ground? What is the, you could say conceptually, what is the value of the land that you're left with compared to the value of the land that you could be left with if you recover all the chromium by a more expensive means? I'm not a cost-benefit analysis expert, but I could see that those things need to be weighed in the balance. And there are experts out there who do that sort of cost-benefit analysis who we collaborate with. So I'm sure we can arrive at an in-depth cost-benefit analysis of the various options for recovering chromium. But I want to go on record as name-checking colleagues at SEPA who prompted the idea that we should be looking at a circular economy approach. Given how much more land at Shawfield and the wider southeast Glasgow district is affected by copra, it warrants a lot more thought and research, we believe.
Okay. We've still got time for a few more. The injection window was 4 meters. Was that 0 to 4 meters from the surface, or at what depth was the 4 meter injection window? How much of the soil deposit profile were you able to inject into?
Okay, so broadly, it wasn't from the surface. Broadly, it was from the water table, which was typically of the order of 2 meters down, down to target depths ranging from about 4 meters to about 7 meters, depending on where we thought where the investigations had shown us the key substances were located. So it did vary around the different parts of phase 1 and phase 2, but not directly from the surface.
And what were the SEPA licensing requirements, and is there a long-term monitoring requirement?
Yes, the licensing requirements are in line with the environmental permitting regulations. So the specialist contractor VHE and their subcontractor Provectus operated under a mobile treatment permit, which, as we know, is carried from site to site and then implemented under a deployment form specific to the job. So their remediation process is set out in the deployment form, and it's underpinned by the risk assessments and the various reports on site investigations and remediation strategy that underpin the process. And there is an extensive and long duration monitoring program required to show that there's no adverse impact from the process taking place, and that the deployment form would not get signed off by SEPA unless the monitoring showed that that was the case.
Okay, and one final question, I think, is if the waste were to be mined again, have you any thoughts on safety measures for that, especially dust generation?
Well, that's a very good question. I think we know, and there'll be many people on this webinar who know more than I do about it, which is mining anything, whether it's coal or chromium or any substance. Dust generation is absolutely a vital factor to control, and we're not in a remote area of Turkey anymore mining ophiolite. We're in central Glasgow mining waste, and clearly dust generation from material laced with hexavalent chromium would be a major challenge. So how that would be controlled would be a major undertaking. I'm not saying it can't be controlled, I'm involved in other projects where toxic substances are excavated in bulk in very built-up areas, and air quality monitoring is relentless. It's very demanding, and trigger levels for various substances in air during an operation like that would be imposed, and operations would have to stop if levels were exceeded. Now, that's a conceptual view. How it would work in practice, I don't know, because we haven't done the research required to delve into to exactly what the process would be. But certainly, air quality and dust would be a vital factor in assessing whether it's actually feasible and environmentally acceptable to open up deep excavations in the way I've suggested.
Great. David, thank you very much for that. That was a fantastic presentation. And just before we close, everybody, I've just got to make a brief announcement. This was webinar number 5. Webinar number 6 will come in January, and this will be by Daniel Quinn from Duscan on Wednesday, the 20th of January 21. So we're having a bit of a break over Christmas. And over to you, Alex, just to close the webinar.
Yeah, just to say thank you very much, David. That's been very interesting. I remember spending 3 years converting Chrome 6 to Chrome 3 in a lab as part of my PhD, and mucking everything up when I didn't quite convert it properly. So it's certainly got some meaning to me. And yes, thank you very much.
Thank you. Thank you for listening.
Great. Okay. Thanks, everybody.
Goodbye.
And hopefully see everybody at the next EIG webinar. And this has been recorded. I'll turn it off in a minute, and this will go onto our YouTube channel. So look out for the post on social. Okay. Cheers, everyone. Okay.
Thank you.
Bye.
Goodbye.
Bye-bye.